Good morning, everybody. Hope you're all healthy and safe. So today we are going to begin with the chapter 10 of our module 3, and in this chapter we shall be discussing about the concept of Banach Algebra and certain theorems related to it. So you all must be familiar with the term Banach Algebra. Still just for the recollection, a Banach space script A is called a Banach algebra if an operation, say product x dot y, is defined for the elements of the space script A which satisfies linearity, associativity, continuity of both the variables in the product, and also there exists an identity element E, which is called as a unity, that is x e is equal to ex is equal to x. Okay, and in this throughout this chapter we shall be discussing, or we shall be dealing with Banach algebra, which is commutative. So commutativity means x y is equal to yx. So this is our Banach algebra, that is a space which satisfies linearity, continuity, associativity, and it has a unit element in it. Okay, so let's move on to the first theorem of this chapter, theorem 10.1.1, and this theorem states that on the Banach space script A, or on the Banach algebra script A, there exists an equivalent norm, say norm star, such that norm star x dot y is less than or equal to norm star x into norm star y, and norm star of unity, that is E, is equal to 1. Okay, so considering the Banach algebra script A which satisfies all the properties, we are saying that there is a norm which is already defined in the Banach algebra, which we can always find a norm which is equivalent to the norm which is already existing and which satisfies the following condition. So we shall prove this theorem. So let us move to the proof of the theorem. So first of all, let x element of script A define a linear operator. Okay, define a linear operator tx by tx acting on y is nothing but x dot y, where y is an element of script A. So this is how we are defining the operator. So clearly tx is linear, there is nothing to prove in that. Tx is linear, right? So because tx of y plus z is nothing but x into y plus z, so that is where x, y, z are all elements of script A. So there where script A is a Banach algebra, so it will be x dot y plus x dot z. So it is clearly linear. There is nothing to prove about linearity. Also, as script A is a Banach algebra, the continuity of x and y implies the continuity of the operation defined, that is here it is continuity of x dot y. Okay, so therefore I can say that this tx which we have defined by tx of y is x dot y is continuous linear operator on script A, and as it is continuous on script A, we can say that it is bounded also. So tx is actually a bounded, therefore tx is a linear bounded operator on script A which is continuous. Okay, now what we are going to do is I'm going to define a map phi from script A to the set of linear operators on script A by phi of x is equal to tx. So tx is a linear bounded operator on A which is continuous, so tx clearly belongs to L of A, right? So I am defining a map with the help of tx denoted by phi from script A to L of A by phi of x is equal to tx. So now let's see one by one the properties. So as tx is linear, I can easily conclude that phi is also linear, right? Okay, now the next one is consider txy acting on z. So this is, by definition, it is xy dot z. Okay, so I can write this as x into y dot z by associativity because all these three elements are belonging to script A. So this is nothing but tx acting on y dot z. Now y dot z, I can again write this as tx ty acting on z. So what do I get? I get phi of xy equal to txy, which is equal to tx into ty. So this is equal to phi of x into phi of y. Okay, next we can also see that phi forms an isometry. Okay, so how is that? Let's see, what is norm of phi of x? We need to show that if phi forms an isometry, then norm of phi of x is equal to norm of x, right? So norm of phi of x is nothing but norm of tx. And what is the norm of tx? This is supremum norm y less than equal to 1 norm x into norm y. So this is nothing but norm x itself because norm y is less than equal to 1. So taking supremum over that, we get this is equal to norm x. So phi norm of phi x is equal to norm x. So phi is an isometry. So we have defined an operator, a linear operator, which is an isometry. Okay. Now what we are going to do is, in the space of linear operators on A, in the space LA, consider the subspace P such that P contains operators of the form B, where B acting on x dot y is equal to bx dot y. Okay, so what we are doing now is we are considering the space L of A, and we are considering, or we are defining a subspace in L of A. Okay, P is a subspace in L of A, L of script A, which satisfies what is the condition of P? That it contains all operators of the form B such that B acting on x dot y is equal to bx dot y. Okay, now we are going to show two properties of B. First one is P is equal to nothing but phi of A. This is what we are going to prove. Okay, so let us choose an element, say tx belongs to phi of A. by definition of phi. Now what is Tx acting on y dot z? I can write this as x dot y dot z by definition. Again, by associativity, it is x dot y dot z, that is x dot y. Again, if we apply the definition of Tx, it is Tx acting on y, right? Tx acting on y dot z. So if Tx is an element of phi of a, I have got that Tx is of the form Tx y dot z. Tx acting on y dot z is of the form Tx of y dot z. So this is implying that Tx is an element of P, because P consists of operators in such a manner that B acting on x dot y is equal to Bx dot y. So here Tx acting on y dot z is nothing but Tx of y into z. So Tx is an element of P. So phi of script A is contained in P. Now conversely, let say B belong to P. Then what do we have? B into Z can be written as B acting on E dot Z. So this is by the definition of B, it is B E dot Z. I am writing this as x dot z, where x is equal to some B. So this is nothing but Tx acting on z, right? So therefore B of z is actually nothing but Tx acting on z. So I can say that B is an element of phi of script A. Therefore P is contained in phi of A. So combining the two results, we get P equal to phi of A, right? Next we are going to show that P is a closed subspace of L. Okay, so let's see how we can do that. Let B element of P, let Bn be a sequence in P, okay, such that this Bn converges to say B. So we need to show P is closed, so we need to show that B is also an element of P, right? So we are choosing a sequence in P which converges to the point B. Then we need to show that the limit of that sequence also element of P. Then P will be a closed subspace. Okay. Now Bn of x dot y is nothing but Bn x dot y for every x and y belongs to script A. Now Bn converges to B, so Bn of x dot y will actually converge to B of x dot y. And also, as x and y are elements of A, they are continuous, so x dot y is continuous. As x dot y is continuous, B of or Bn of x dot y should converge to B of x dot y, right? So Bn of xy is a sequence. Bn of xy is converging to B of xy. Also we have seen that Bn of xy is converging to Bx dot y. So therefore, since by continuity and limit, the limit must be equivalent, so we get B of x dot y is nothing but Bx dot y. So this implies B is an element of P, and hence P is closed. Okay. Now what we do is we are going to define the new norm. Okay. Now consider norm star x is equal to norm tx. This is how we are going to define the new norm. Okay, so let us see whether it satisfies all the condition. Now norm star x is equal to norm tx. So this is the old norm which is already existing in L of A. So this is greater than equal to 0. Therefore norm star of x is also greater than equal to 0. Now when will it be equal to 0? Now suppose norm star x is equal to 0. This implies norm tx is equal to 0, which further implies norm x dot y is equal to 0. So this is x dot y is 0 because this is a norm which we have already defined. This is true for every y belongs to script A. So if I choose x dot y to be E also, this is true. So this implies x is 0. So norm star of x is always greater than 0 and norm star of x is 0 implies x is equal to 0. This is an if and only if condition. Okay, so the first condition of the norm is satisfied. Now let's move on to the next one. Triangular inequality, norm star of x plus y, or here it can be is nothing but norm of tx plus y, which is equal to norm of x plus y dot z, which is nothing but norm of x dot z plus y dot z, which is further less than equal to norm x dot z plus norm y dot z. This is further equal to norm tx plus norm ty. So this is norm star x plus norm star y. So we have got norm star x plus y is less than or equal to norm star x plus norm star y. Similarly, the last one, the third property, that is norm star lambda x. This is nothing but norm of t lambda x, which is nothing but norm of lambda x dot y, which is by normal condition. This is norm of x dot y, which is nothing but norm tx modulus lambda into norm star x. So all the three properties of the norm is satisfied. So all the three properties of the norm is satisfied. So hence forms a norm in script A. Now we need to show that this is equivalent to the norm which is already defined. Okay, so for that what we are going to do is, first we shall show that script A is complete with respect to this norm, with respect to norm star. How can we do that? Okay, we have the map from script A to the set of linear operators on L of A. Okay, phi is a mapping from script A to set of linear operators. Then as A is Banach, so will be the set of all linear operators on A. Okay, so L of A is a Banach space, and we have obtained that P, we have chosen P to be a subspace of script L of A. Okay, and P was closed. So we know a result, the closed subspace of a complete space is complete. P is complete. P is a closed subspace of L of A, and since script A is a Banach space, L of script A is also a Banach space, so P is complete. So we know that phi of script A is equal to P. So phi of script A is complete. Thus, by considering the map from A to phi of A, okay, it is onto surjective and an isometry. So if phi of A, so as phi of A is complete, script A is also complete. Okay, so we have used the concept that P is equal to phi of A and P is closed to prove that script A is complete with respect to the new norm that we have defined. Okay, now what was how did we define norm star of X? That was nothing but norm of Tx, and this is supremum norm y less than equal to 1 norm of Tx acting on y. So this is nothing but supremum norm y less than equal to 1. By definition, this is x dot y. So norm star X is nothing but supremum of norm x dot y. So this implies norm of x dot y will be less than equal to norm star of x, right? So I am choosing this y as E by norm E, because E by norm E means norm of y is equal to 1. So I can replace y by this. So this is also less than equal to norm star. So this is true for every norm y less than or equal to 1. So if I choose y to be E by norm E, then norm of y is equal to 1. So it's true in this case also. So this implies norm x dot E by norm E is less than equal to norm star x, which implies norm x dot E is x itself, E is a unity, norm of E is 1, is less than or equal to norm star x. So we have got two norms on script A. Okay, let me just write it down. So there exists norm and norm star on script A. Script A is complete and norm of x is less than equal to norm star of x. Hence, just look into corollary 9.2.3. 9.2.3, we can conclude that these norms are equivalent. Okay, so we have got an equivalent norm in script A. Okay, now we need to prove two more conditions, that is norm star x dot y is less than or equal to norm star x into norm star y, and norm star of E is equal to 1. So first let's see what happens to norm star of x dot y. So this is nothing but norm of txy, right? Now we know, we have just now seen that txy is nothing but tx dot ty. So this is less than equal to norm tx into norm ty, and this is equal to norm star x into norm star y. This is our old norm and this is the new norm. So in the new norm also we have norm star x dot y is less than or equal to norm star x into norm star y. And the second one, that is norm star of e must be equal to 1, right? Norm star of e is nothing but norm of te, and norm of te is what? It is nothing but the identity operator itself. Te means it is the identity operator, and what is the norm of the identity operator? It is 1. So this is the proof that there exists an equivalent norm in the Banach algebra which satisfies these two conditions. Okay, so there is just another remark that I would like to mention, that is, if norm xy is less than equal to norm x into norm y, and if norm of e is equal to 1, then norm star x or norm star is equal to the norm. Okay, they both are equal if these two conditions are satisfied. This is in case of old norm. So let us see how we can prove that. Now, norm of x can be written as norm x dot e, very easy unity. So this is nothing but norm of tx acting on e, and this is less than equal to norm tx into norm e. So this is norm of tx, and by definition this is nothing but norm star x. Okay, so I have got norm of x is less than or equal to norm star of x. And now let's see what is the definition of norm tx. Norm tx is nothing but supremum norm x dot y, where norm of y is less than equal to 1, and this is less than equal to supremum of norm x into norm y, because we are given the condition that norm x y is less than equal to norm x into norm y, where norm y is less than equal to 1. So this is nothing but norm x, right? So therefore what do I get? I get norm x is less than or equal to norm star x is less than equal to norm x. So this implies they must be equal. So this was an arbitrary x, so hence these two are equal. Okay, so this was about the first theorem in our chapter 10, that is, we can always find an equivalent norm which satisfies these two conditions, and we have also seen a remark related to the same. So the next few theorems and discussions will be held in the further lectures. So that's it. Thank you. Stay safe and stay healthy.